All right, so first thing that we're going to calculate is, let's see, what's the simplest type of configuration? Simplest type of configuration is actually a ring. Thanks, man. So, and while this is actually booting up, I can go. Yeah, because interestingly enough, demonstrating an electric field is extremely hard. Usually, what teachers end up doing is they end up looking at magnetic fields and using magnetic fields and the field lines generated from magnetic fields as a teaching device for electric fields. And I think it's a bad idea.
That's like with the race crystals.
Yeah, you'll see. I've ordered a magnetic field viewer, so you guys can see it. So if you were to look at the electric field for a set of point charges, it's going to be the sum of kq over r squared. And by the way, for you guys, for your homework, your k can be expressed in there's a different expression for k. That's 1 over 4 pi epsilon naught. So you might see me use these interchangeably. I would say put this in. Instead of using k, use 1 over 4 pi epsilon naught. I guess so, yeah. Or you just write it down, just show it to me. I think it might be a little easier. I think I might avoid using those types of algebraic expressions. Yeah. So it's basically just a different constant. In other words, k equals 9 times 10 to the 9th, and its units are what? What are the units of k? See if you guys remember. Well, if you multiply this by q, right, then you have force, right? So then what would the units of k be? Clearly it has to cancel out what in the numerator? Yeah, so it's going to be Coulomb squared in the denominator, and it has to cancel out the meters in the... There you go. So then... Clearly, epsilon naught would just be the inverse of this. And it's 8.85 times 10 to the negative 12. There's reasons why, and you'll see this when we get to Gauss's law, there's reasons why epsilon naught is used when you get into your second course. So, if you have, let's say, some discrete set of charges, then the electric field from that discrete set is going to be the sum, right, of your 1 over 4 pi epsilon naught times qi over ri squared, where each of those are in what direction? Yeah, they're in the ri direction. So this is the sum of a set of point charges on some test charge. Now, how would I go and take this to the continuum? In other words, what is going to change if I go from a set of discrete charges to a set of continuous charges?
Is it like the bar?
Well, it's not going to be sum. It's going to become a... Well, the sum becomes an integral, right? Because the integral is just a continuous analog of sum. And so instead of your qi, that's going to become your dq. In other words, your element you're summing up over each of these little infinitesimal elements of charge. And each of those infinitesimal elements of charge are how far away from the point charge or the test charge. They're each r squared away.
This is for, what is it?
This is for the electric field generally. And all of them are in what direction? In the r hat direction. So this is the electric field due to a continuous charge distribution. Notice it's a vector quantity. So to see how this works, I'm going to do the simplest case. And the simplest case would be a ring of charge. So something like this. And I'm actually quite curious if I could set this up. I'm pretty sure I should be able to. All right, I should be able to set up a ring of charge. How would I do this? I use a Van de Graaff, connect it to here, right? Like, if I remove this stand, right? And then I should be able to see how this affects what? Maybe a pith ball, right? Because what would that do? Although a pith ball would be kind of difficult. But you can see in principle how to set up a ring of charge. It's one of those, remember those small balls that hang on a string? They're like styrofoam. They're coated with conductive, like a conductive paint. It's something I might consider. But right now I just want to actually demonstrate how this works. Because once you see it once, then it becomes obvious. So take a ring. So here's your ring. And generally speaking, for your first problem, you want to find out what the electric field is at some point along an axis that passes through the center of the ring. So you pick a point. So let's say this ring has some radius. R. And you want to find it at some point x. Notice I used capital R to describe the radius. So how can I find the electric field? Well, the first thing you have to realize is that this is a vector, right? So first thing, when you go and approach these problems, you have to first exploit any type of symmetry that exists. And why would you want to do that? Because if you didn't do that, then you'd have to show how the electric field varies in each direction. And generally speaking, you're only going to be finding electric fields for highly symmetric situations. So if I were to ask you, I take some element there. In other words, this charge is smeared over this ring. And so I take some tiny dq here. And the question is, let's suppose it's positive. Where is the direction of the electric field at point x from dq? Think about it. I'll talk to each other. Which direction does the electric field from this dq point?
Oh, wait, DQ is positive, right?
Correct. It's a positive charge. Talk to each other.
So, like, ignore the rest of the ring or factor in the rest?
No, just that one piece. Just that one piece. Where is it going to point?
Like an infinitesimal.
Yeah, just one slice at the top. So which direction do you think it is? Okay, so in other words, it would be directed along what? Okay, so what Jake says is that it should be directed. It should be directed like this. Oh, you are really right. So that means your electric field is directed in what direction? At an angle like that, right? So If you go on the exact other side of this ring, where's that electric field pointing? So in other words, you go on this side of this ring. That's right. So in other words, on the other side, it's going to point at this angle. All right, so the other side, it's going to point on this angle. Right? So then if you integrate over this whole, and furthermore, if you, let's say this side, where's this side going to point? It's going to point like that way, right? And this side is going to point that way. So when you sum up over each of these charges, where is the net electric field going to point? Straight out. So that is the component that survives. And so let's just calculate that to begin with. To some degree, yes. Yeah, to some degree, yes. I've never thought of it that way, but it's something I'm going to consider looking at. I'm still looking into the lightning question, by the way. So let's call this alpha, right? And so therefore, this angle's alpha and this angle's alpha. So we can just erase this angle and just look at this. So this is how's that? Is that clear? So this is the DE, points this way, right? But the only component that survives is the component along the x-axis, which you call DEX. And so what's the relationship between DEX and DE? It's cosine alpha. In other words, DEX is equal to DE cosine alpha. And remember, DE is just another way to write everything in here without the integral. So it's equal to dq over r squared r hat. So what do we have? We have that this is equal to dq over r squared, right, times the cosine of alpha. And what direction is this going to be pointing? In the x hat direction. So now, the question is, does the electric field change depending upon where each of these elements are? Like when I go and sum over dq, is any dq further or closer to x? Meaning that each piece of these elements of charge are equidistant from x. So what that tells you is that then it's a constant. In other words, when you sum over all the charge across the entire ring, it doesn't matter how far each of those are away. It's just going to be a simple sum. So, but let's first figure out what little r is. What's little r? That's the hypotenuse. That's right. So therefore, r squared is equal to what? So it's going to be x squared plus r squared.
You wouldn't want to do it like the sine of
No, you'll see. So what do we have here? Now dq, when you go and, so before I go and do this, what is the cosine of alpha equal to? It's equal to x over little r, right? Which is equal to x over the square root of x squared plus r squared. So what do we have here? We have that it's dq times x over x squared plus r squared to the 3/2.
Oh, okay. Wait, can you explain that real quick?
Because this is x over little r, correct? So then you have x over little r cubed, but little r is the square root of x squared plus big R squared.
Okay, yeah.
Why'd you add dq after?
Because it's still in there. I have not expressed dq as a function of any of these other parameters. So it's still in there. That dq comes from dE. So we're still only looking at this contribution. Now the question is, does any of these depend on x or r? When I go and sum up this charge, does it depend on any of those parameters? Yes or no? No, it's independent. In other words, if I were to ask you, what is the sum of all those charges? Well, generally speaking, when you're looking at continuous charges, you don't look at it in terms of saying Q. You say this thing has a linear charge density. And that linear charge density, let's make it constant. The linear charge density is lambda. And what is lambda defined as? Charge per unit. Well, in this case, it's going to be charge per unit length. Or more specifically, lambda is equal to dq dl. And why am I using dl? Because what is the length with which charge is being summed over? Meaning which length am I summing it over? The arc length of this, or the circumference. So therefore, if I told you that this thing has uniform charge density, lambda, then we replace dq with lambda dl. So what we end up with is x times lambda dl over x squared plus r squared to the 3/2. And the question is, does dl depend on x or big R? Does it?
It's big R.
Big R times dl.
Yeah, wait.
What is arc length equal to?
DL is the circumference, right?
dl is not the circumference, the arc length.
So
What's
it's
arc length?
pi.
Nope, you're one step ahead of the game. dl is equal to r d theta. Right? When you go and you look at some arc length, this arc length, dl, is located how far away from the origin? R. So this is r. And what angle from the origin? D theta. Or you actually, technically, you would say this is r, and that slice is d theta. And notice each of these dl's are equidistant. So you sum over all of them, and what do you end up with? 2 pi r. And there you have it. So what we end up with is x times lambda times 2 pi r over x squared plus r squared to the 3/2. And of course we have the 1 over, I'll always forget the 1 over 4 pi epsilon naught. That just goes through all the way. No, what you're doing is you're summing up all of these little charges, all of this charge. This charge, this length that you're summing over, is independent of how far your test charge is away. Now, this isn't obvious because guess what? We're going to be dealing with other distributions where it's not. Like, for instance, can anyone name a distribution where the charge is located is not independent of how far away your test charge is? Imagine this has uniform charge distributed over it, right? Imagine my test charge is here, right? Are each of these infinitesimal charges the same distance away? No, right? This infinitesimal patch is closer, right? Because it's spherical. This has that additional dimension. And not just a sphere. Not just a sphere. What about, no, it can be any 2D. What about disk? Right? Yeah, in other words, see this disk? This piece of the disk is closer to that than this piece. So, well, this would be a 2D plane. Even on if it's a 2D plane, we're going to go back to this and we have to see the limiting behavior.
Right. Like here, it wouldn't make a difference? Or it would, right?
No, it would.
Okay.
Because this point is closer than this point.
Yeah. Okay.
But it just so happens that this ring, later man, every point, have a great weekend. Yeah, today's a weekend. Every point that you're summing up the charges is equidistant from this point right here.
Okay. Okay. So then
And so therefore they're all independent.
And then we're going to look at what if it's off-centered.
Yeah, we're going to, well, actually no, for the ring, you just leave it as a ring. We're going to look at the disk next. Then from the disk, you go to the line. You'll be able to start them soon.
Okay.
Later.
Good.
Yep.
Which,
Yes.